Hi, today I'm going to talk about relative motion. Just like other motion analysis, it involves displacement, velocity, and acceleration, as well as angular velocity and angular acceleration. Basically, relative motion is a relation between a particle and another reference point or a particle. In this video, I'm going to be showing you examples regarding 2 points on the same rigid body, which is very easy compared to 2 points on a different rigid body. Two things to remember when doing relative motion analysis is that different points on the same rigid body have the same angular velocity and angular acceleration, but different velocity and acceleration. Another point to remember is that a fixed point will have zero velocity. Next, we will be looking at the formula that we'll be using in relative motion analysis. The first formula is the displacement equation. It is given by RB equals to RA, which is the reference point, plus RB with respect to A. If the reference point is the origin, then RB is equals to the distance from the origins to point B. The second formula is the velocity equation. It is the time derivative of the displacement equation. As you can see, it's just the same as the displacement equation, except that it is in velocity terms, which is Vb equals to Va plus Vb with respect to A. Since the relative velocity Vb with respect to A represents the effect of circular motion about point A, this term can be expressed by the cross product Vb with respect to A equals to omega of AB cross with Rb with respect to A, and it is shown as follows. Next, we will look at the third equation, which is the acceleration equation. It is the time derivative of the second formula, which is the velocity equation. As you can see, the equation is similar as before, except it is in the acceleration terms. However, this time, we divide the acceleration of b with respect to a into two terms, which is the tangential and normal. Just like before, like in the velocity equation, we can express the relative acceleration in a different form. Since the relative acceleration components represent the effects of circular motion observed from translating axes having their origin at the base point A, these terms can be expressed as acceleration of b with respect to A in the tangential form equals to alpha cross with Rb with respect to A, and acceleration of b with respect to A in the normal form equals to negative of omega squared times with Rb with respect to A. Enough of the derivations. Now we will look at some examples. But before that, I would like to share with you some tips in solving relative motion analysis problems. Well, to be honest, there's no tips actually. It's just that you need to remember the three equations that we discussed before, which is the displacement equation, the velocity equation, and the acceleration equation. With these three equations, you can easily solve any problems related to relative motion analysis. It is valid for all the problems which involve relative motion analysis. So don't worry, just remember the three equations and we're done in solving relative motion analysis problems. Now let us look at some examples. The first examples involve only velocity, while the second example will involve both velocity and acceleration. The first example is as follows. If velocity of A is 2 meters per second downward, determine the velocity of B at the instant theta equals to 45 degrees. Before we start solving the question, let us list down all the information given in the question. The first one is the velocity of A, which is the negative 2 in J direction. The second and third one is the relative displacement of point B and point C from point A. The relative displacement of point C is not that important because we only want to find the velocity of B, but not the point C. Next, just as before, we use the tip, which is the velocity equation. Looking at the formula, we have VA, we have RB with respect to A, and we want to find VB. We insert all the values in the formula. We know that VB is moving in the I direction, so we can say it as VB in the I direction. And then equating the I and J component, we will get the omega and velocity of B, which is 14.1 radian per second and 2 meter per second respectively. If you want to find the velocity of C, we can just use the same equation. Just change the B with C, which is Vc equals to Va plus omega cross Rc with respect to A. It's as simple as that. Now let us look at the second example. This example involves both velocity and acceleration. The question is as follows. Before we start solving the question, two things that we must remember is to list down all the information given and the two formula, which is the velocity and acceleration equation. These two things are very important so that you won't make mistakes and forget them. Looking at the acceleration equation, we need to find omega first before we can proceed further. To get the omega, we use the velocity equation. The step is the same as in the previous example. It is as follows. By doing the I and J component, we will get the VB and omega of the ladder. By having the omega, we can now proceed to the acceleration equation. The steps are the same done in the velocity equation. Notice that the alpha is in the negative direction. This is because the ladder is rotating in the clockwise direction, which is in the negative direction. By solving the equations, we can now get the alpha and acceleration of B, which is 0.634 radian per second squared in the clockwise direction and 5.178 meter per second squared in the downward direction. See, with these two equations, we can simply solve relative motion analysis problems. It's that simple. Just remember to have these two equations in your head.